So, our schedule got thrown off a little bit because of football. Um, so, um, but thankfully not affected too much because I had some slack at the end of a schedule anyway. So, today will be the last day I spend on chapter 4 in notes, which is basically solving AX equals B systems that come up from elliptic or time independent problems like Poisson's equation. And then the rest of the material, chapter 5, will be on time dependent problems. And what I'll probably do next week or so is there's still a little bit more to add to the notes, like stuff I haven't covered in this class before. And that also means composing what will be the fourth and final homework assignment, which there won't be much to it, like probably just 2 problems. But okay, so but yeah, so I think we'll have roughly, including today's, I think 6 more classes of covering stuff. So if we end up having class periods past that point, well, there's nothing to do with homework questions. So, and you guys can ask me that whenever, as needed. Because there haven't been very many questions all semester long. But thank you for submission. I'll look at it later when someone else submits too. Anyone. Okay. All right. So it's been nice not having much of a grading burden so far, but that means it's probably going to be a lot at the end, but at least I know it's coming. Okay, so when it comes to solving AX equals B, it comes from a PDE, generally a sparse matrix, especially if using like finite difference methods. We've seen some types of methods already, like direct methods such as Gaussian elimination or Cholesky factorization. Also, stationary iterative methods such as Jacobi or Gauss-Seidel. So they, and then we also saw multigrid. So the last category are of iterative methods. Krylov subspace methods. Okay. For embarrassingly many years, I was pronouncing this wrong. I would say Krylov. Based on nothing except for the popular brand of spray paint called Krylon. So okay, Krylov. Oh, it's Krylov. I was like, whenever someone refers to a very famous prolific mathematician, Leonard Euler, instead of Euler, yeah, that just drives me insane. So, yeah.
He was blind in his right eye.
He was?
He was blind in his right eye.
Oh, I didn't know that.
Yeah. Every picture that is of Euler is.
Oh, okay. Huh. It's all more remarkable that he published over like 800 something papers in his lifetime. But I had to wonder, like, okay, so, but again, one of those papers could have been like, where he introduced Euler's method for time-dependent ODEs, the simplest time-stepping method of all, which actually I'm going to cover probably next class. And it's like, wow, the bar to get a paper published is so much higher these days. So, like, I feel jealous of all those mathematicians from long ago who had very little to build that had already been developed, so they could just go ahead and swoop in and develop it.
You have to do a lot for it to.
Yeah.
Here you could do a little, and it was like, hey, nobody's done this.
That's true.
Yeah, it's quite sad. Because,
Talking of pronunciation, this mathematician, Cauchy,
Cauchy. Yeah.
I'll say Cauchy.
Oh, well, what about him?
Cauchy, I mean the pronunciation.
Oh, okay, yeah.
Those coche or
Yeah. Well, on a TV series several years ago, the series was Rizzoli and Isles, which are based on murder mystery books that I enjoy. But so the actress playing Dr. Isles made a reference to, and this is what she actually said, like Euler's formula relating the three most important numbers of mathematics. Like, no, it's Euler's, and it relates to five most important numbers in mathematics.
important numbers. One is 0.
Yeah.
E to the I pi plus 1 equals 0.
Ah, okay.
So I guess if you, I'm
Like,
trying to think, how can it be only three numbers then? I mean, if I write e to the I pi equals minus 1, then it's four numbers. So yeah,
these
so,
zeros, these
so-
ones?
I mean, could that screenwriter done a little bit of research? Well, like in the movie Good Will Hunting, it's about Matt Damon plays a mathematical prodigy, um, and uh, um, so they actually hired a mathematician from Caltech to do the mathematical writing on the board, just so it'd be legitimate stuff. I mean, nothing special, but yeah. Okay. Oh boy. All right. Now, all right. So that's Krylov subspace methods. Okay. All right. So, we're solving AX equals B. And we're going to assume that there's no need to perform preconditioning on this system. In other words, the matrix A is reasonably close to identity, or at least it's well conditioned. So then we have this iteration, xk plus 1 equal to xk plus rk. And to refresh your memory, rk is the residual. Okay. And also to refresh your memory, this is based on what we saw for a general preconditioned iteration. Preconditioner times dk is equal to rk, where dk is equal to the step from one iterate to the next. So this iteration is equivalent to this one, where the preconditioner P is just identity. In other words, we're not bothering with preconditioning. Okay. Now, so what I can do is, if I set my initial guess, x naught, this be 0, then what I can do is, since the formula for each new iterate is fairly simple, I can write out formulas for the iterates to come. So what would happen is x1 would be x naught, which is 0, and then the residual, in this case, would just be b. So x1 is just b. Okay, then x2, if I substitute x1 equal to b, I'm going to get b plus b minus ab. So I end up with 2b minus ab. All right. And then if I continue process x3 is equal to 3b minus 3ab plus a squared b. Okay. So what we see is each new iterate is a polynomial of a times b, because I can factor a b out of each one of these. No. Now, so in general, and you probably guess what the formula is going to be based on the nice patterns of the coefficients. It's kind of reminiscent of Pascal's triangle. Xk is equal to some polynomial of degree k minus 1 of a times b. Yeah.
Can you say, go over again to see how we got these, so
Oh, all I'm doing is I'm taking,
times b minus,
so all I'm doing is I'm taking this and plugging in for xk, and also plugging in here to get the residual. So for example, when
b,
x1 is equal to b, I get b, so x2 is equal to b plus b minus ab.
b, so 2b minus.
Yeah.
And then we plug,
And then I plug that in for x2. So I'm going to have 2b minus ab here. And then plus b again, plus 3b, minus a times this.
okay,
Okay.
so 3 times.
Yeah. Okay. Right. Now, so what we can say is xk belongs to the span of these vectors, b, ab, a squared b, so you start with b, and you keep multiplying by a, all the way up to a to the k minus 1 times b. So it's also the space of all, it belongs to the space of all polynomials of a up to degree k minus 1 times b. And this kind of subspace, all right, so I'm going to give it a name, capital K. So subscript k is the dimension of subspace. Because you can see we have k vectors in here that's describe the basis. So it's a subspace that's generated by b through multiplication by a. And this kind of subspace where you start with a given vector b and you generate the rest of the subspace by continuing to multiply by a up to a certain point. This is called a Krylov subspace. So any subspace that has a span of these kind of vectors, a vector multiplied by a certain matrix a certain number of times, that's a Krylov subspace. Okay, now, what I'd like to do, I have a statement here in my notes about when an iteration like this is going to converge. But I'd like to see if it's possible to actually prove that for you instead of simply giving the result. Just because these polynomials follow a fairly nice pattern. And to see what that pattern is, like, okay. Well, okay. What I'm going to do is I'm going to subtract from both sides the exact solution x. Actually, all right, I'm going to do this on a fresh board because I'm about to run out of room. Okay. So, to repeat, x3, well, I'll subtract off the exact solution x. Now, x is equal to so minus x. Now, the exact solution x is equal to A inverse B. So I'm just rewriting x as A inverse B. And then the rest of the expression is plus 3b minus 3ab plus a squared b. All right. So this is the error. Okay. Now, what I'm going to do with each of these terms, I'm going to throw in an A inverse. So because that'll be identity. So I have minus A inverse B plus 3A inverse B minus 3A squared A inverse B, A inverse B plus A cubed A inverse B. Now, A inverse B, because that's just simply X. So I can factor out an A inverse B, all right, and also pull out a minus. So what's left? I'll have identity minus 3A plus 3A squared plus A cubed. Whoops, that should be a minus. Okay.
A inverse B was.
Yeah. Yes. Now that polynomial, identity minus 3A plus 3A squared minus A cubed.
A whole cube.
Sorry, what?
I minus, no, oh, sorry. I minus A whole cube?
Oh, yeah, you factored it?
Yeah.
Yes. That's what I was gonna ask you to do, can you factor it?
I just know the formula.
Well, good. That was helpful. So minus identity minus A cubed X. Okay. So the error, so in general, xk minus x is equal to minus identity minus a to the kth power times x. So we want to be sure that this error goes to 0 as k goes to infinity. And so this came up before with stationary iterative methods, where in that case also the error your error results from multiplying by a particular matrix. Now in case of stationary iterative methods, the matrix was M inverse n. So this means the error goes to 0 if and only if the spectral radius of identity minus A is strictly less than 1. Which is also true if and only if lambda minus 1 in absolute value is less than 1, where lambda is an eigenvalue of A. So, for instance, if a matrix A was symmetric, and therefore the eigenvalues are real, the eigenvalues would have to lie between 0 and 2 for this to work. So this iteration would only work if, like I said, we're making the assumption that the system is already preconditioned. In other words, the A is reasonably close to identity, and certainly if the eigenvalues are all near 1, then that's what we have. Okay. Any questions about that conclusion? Now, if we do have preconditioning, then we have this iteration, preconditioner xk plus 1 minus xk equals residual rk. So same iteration, except now we have this p in front on the left side. So what ends up happening is xk belongs to a Krylov subspace of dimension k, generated by P inverse B, and we keep multiplying by P inverse A. So what that means now is we need the spectral radius of P inverse A minus identity is less than 1. Which makes sense because in preconditioning, you want a preconditioner so that P inverse A is close to identity. All right.
Can you please go over the second one?
Oh, wait. What?
Please go over the second one. Yeah, the second one.
Oh, this one?
Yeah. Okay,
So, in other words, if you start with vector P inverse B and you keep multiplying by P inverse A, the xk is in a subspace spanned by those vectors. Yeah. So before we had a Krylov subspace generated by B multiplying by A. Here it's the same thing, but so in other words, my iterate would look just like this, except wherever you see A, it would be P inverse A. Also, wherever you see B, it would be P inverse B. questions about what we have here? Okay. Okay. So this is one kind of method in which the iterates belong to a Krylov subspace. So now I'm going to talk about more general Krylov subspace methods and why they could be very good methods to use, at least for certain problems. Um, okay. So, the properties of Krylov subspace methods. First, each iterate okay, belongs to, or I should say, each iterate minus the initial guess. Now, usually if the initial guess is just chosen to be default vector of 0, but in case there is an initial guess, xj minus the initial guess belongs to the span of these vectors that define a Krylov subspace. All right, so let's see. Krylov subspace of dimension k. Oh, I didn't even notice this text here before. Was that here the whole time?
Yeah.
Yeah.
Okay. Yeah, somebody forgot to turn something off. Okay, whoops. Oh, that was Dr. Chen, actually. I think he was in here last. So, all right. Well, this didn't get in the way. All right. And the thing is, knowing that each iterate is of this form can be very helpful in terms of finding, because making sure a vector is in the subspace still leaves infinitely many possibilities. But knowing it's of its form can help you find the best choice from that subspace in some sense. Okay. Because the subspace is extended just by multiplying by A. So during each iteration, the most expensive operation that you perform is you multiply by A. It's a matrix. So it's often abbreviated, like colloquially, as a MATVEC, matrix vector product. And now matrix vector multiplication normally is order n squared floating point operations if A is n by n. But we're interested in problems for which A is sparse. So if a matrix A comes from a PDE, and therefore is sparse, for example, finite difference or finite element method, and methods like that, then this MATVEC operation requires order n floating point operations instead of the default n squared, just because of the sparsity. Or it could be n log n if this is a spectral method and you're using BFFT. So it's still pretty cheap. All right, so that's one of the nice things about the Krylov subspace methods the iterations are fairly inexpensive. Now, you want to make sure the method still converges rapidly, or you'll be performing a lot of iterations, and that would be bad. But at least you don't have much expense per iteration. Okay. Okay. Now, I was going to give some examples of Krylov subspace methods. Okay. And also for criteria that defines them. So the criteria for choosing the next iterate. So one example is you require that the residual be orthogonal to the Krylov subspace of the same dimension. So the kth residual should be orthogonal to the Krylov subspace of dimension k that is generated by B and A. And a method that uses this criteria is CG, or conjugate gradient, which I'll be talking about a lot more later, as time permits. Now, some of you may have heard of what's called the method of steepest descent. In that case, each new iterate, you just follow a direction of residual, and you find a vector along the dimension of residual that gets you closest to the solution. But in that case, each residual is only orthogonal to the previous residual, which is not good because you actually it creates like a zigzag effect in your iterates and can lead to slow convergence. But here, residual is orthogonal basically to all previous residuals. So that's a significant improvement. Yeah. Okay. Another criterion is this minimizing the norm of a residual among all vectors in the Krylov subspace. And that is a criterion used by a method called GMRes, generalized minimum residual method. And also its close relative MinRes. MinRes actually is GMRes specialized to symmetric matrices, which leads to a simpler method. So MinRes requires symmetry. Conjugate gradient is only for SPD, symmetric positive definite matrices. But those matrices are important in certain applications. Of the finite difference matrices we've been dealing with are symmetric positive definite. Whereas GMRes can be useful for any kind of system. So I mean, square, invertible, but doesn't require any kind of symmetry.
What is GMRes?
Generalized minimum residual method. And there are MATLAB functions that implement all of these. So actually, the MATLAB function is GMRes or MinRes. For conjugate gradient, it's called PCG, preconditioned conjugate gradient, because most times you really shouldn't use conjugate gradient without a preconditioner. Okay. Another criterion which is related to the first one is that each residual is orthogonal to a Krylov subspace generated by A transpose. And this is for a close relative of conjugate gradient by CG, by conjugate gradient, which is a generalization of conjugate gradient for non-symmetric systems. And finally, another kind of criteria is to minimize the error in a two norm. And this is a method called SymLQ. It's for symmetric systems that are not necessarily positive definite. And it's actually developed by, I guess you could say, my academic brother, Michael Saunders, who's still at Stanford. So he and I had the same advisor, Gene Golub, except that Saunders was advised by him like a zillion years before I was. Like 30 years or so. Yeah.
The third one, is it the Krylov subspace?
Yes.
Okay, B, A transpose?
Yeah, so it is. Here you take B and keep multiplying by A. Here you still start with B, but you keep multiplying by the transpose. Yeah, so in other words, it's a span of B, A transpose squared B, and so on.
But how does that look in terms of the residual? Was orthogonal to every before that, no.
Yeah, so the residual is still B minus AX. So either way, it's orthogonal to a increasingly large subspace. And the idea is if eventually you make residual orthogonal to the whole space, then it must be zero.
Okay.
But even though you're not going to take very many iterations, but hopefully residual is at least small by being made orthogonal to a large space.
What kind of relationship does the first and the second space would have? BA and BA transpose.
I'm not sure how related it'd be to one another.
That's what
I think just because since in biconjugate gradient you don't have symmetry, so it's generally more convenient to work with a transpose. So I guess you could argue that really both conjugate gradient and biconjugate gradient use this, except when it's conjugate gradient, A transpose is A. So. All right, now, I have some further material on just, well, the rest of the time is going to focus on conjugate gradient. Okay, first, any questions about this? You might have noticed I'll show them homework, but although I'll talk more about, because the last other component of this course is, of course, the oral final exam, and anything that's discussed in the notes is fair game, where I will look through the notes to think of questions. Okay. Well, I only have 28 minutes left, so we'll see how far I get. Conjugate gradient is actually one of the most difficult topics, new methods to discuss. Right. So we'll see how it goes. So, conjugate gradient. All right. So, this is required that A is symmetric, positive, definite. So residual, RK, is orthogonal. The real subspace of dimension K generated by B through continued multiplication by A. Now, but the thing is, residual, RK is defined to be B minus A xk. Now, so if xk belongs to this Krylov subspace of dimension k, if we multiply by A, that is in the next Krylov subspace of dimension k plus 1. Okay. All right. Now, I'm going to assume that the Krylov subspace of dimension k is spanned by these vectors that I'll label Q1, Q2, up to Qk. And I'm going to assume that these vectors are orthonormal. All right, so for each index k, we have that orthonormal basis that describes each Krylov subspace. So in that case, that tells me that my next residual RK is going to be some scalar multiple of the next such vector. Because on one hand, RK belongs to the next Krylov subspace, but it's orthogonal to everything in the current Krylov subspace. So it must be a multiple of a one vector that differentiates these two. So in fact, that's how I can get the next vector in the space, is I know it's a multiple of a residual, because a residual I can compute. Okay. So this tells me that each residual is each previous residual is orthogonal to the current residual. All right, so for all indices I that are less than k, we have this. So, and this is what I was saying earlier. Each residual is orthogonal to all previous residuals. Okay. What?
Is that done?
Is what?
Okay. Underneath orthonormal.
That's fine.
Oh, this is an implies.
No. Is it that?
That's the gamma k. Yeah. Still don't figure out what you're pointing at, but
No, it's R and then gamma, so sometimes somebody writes R like that.
oh, I see. Oh, like a fancy. Oh, okay. So reason why R is very uncurvy. Well, like how I'll write a partial derivative symbol and people think I'm writing a 2.
I have mistaken that.
Okay, yeah.
Once I was
Yep. Okay. Oh, speaking of del, actually delta is going to be easier. So I define delta Ri being the change in the residual. And I'll also define delta X I to be a change in X. Okay. I know in the past I've had some mistakes in these notes. Hopefully I've fixed them all by now. Okay. The RK is in K plus 1. Okay. Now, remember that RK is in Krylov subspace K plus 1. Well, this, therefore, must belong to a Krylov subspace of dimension I plus 2. So it's always one more than the index. So this vector belongs to Krylov subspace I plus 2. I'm leaving out the BA part because the only Krylov subspace we're dealing with is one that's generated by B through multiplication by A. All right. And then this vector belongs to Krylov subspace I plus 1. So each x belongs to a Krylov subspace with the same index. Each residual belongs to the Krylov subspace with the next index. Okay. All right. Now, because each residual is orthogonal to Krylov subspace of the all indices less than or equal to its own. So that says that delta Ri, make sure I get my indices right. No. Okay. Yeah. Delta Rk transpose delta Xi must be 0 if I is less than K. Reason for that is this residual is this change of residuals is the difference of these two residuals. This is orthogonal to Ki plus 1. This is orthogonal to Ki. So both of these are orthogonal to Ki. So a difference certainly is too. But if this delta X has a smaller index than K, then it belongs to the very subspace that this is orthogonal to. So it must be 0. All right. Yeah.
Delta Ri is belonging to Ki plus 2 or
I plus 2. Yeah.
2?
Yeah. Okay. Just because this belongs to Ki plus 1, but this is orthogonal to K plus 1. So, all right. Yeah. Oh, wait. Oh, sorry. This is orthogonal to K. Right. So that's why if I is less than, okay. Okay. Now, but the thing is, what I can do with delta Rk so that's equal to B minus A xk plus 1. So that's the first residual being subtracted, minus b minus axk, the second residual that's being subtracted. But then if I simplify all this, the b's cancel, and what I'm left with is minus a delta xk. So now if I take that and substitute that in here, I get this very important conclusion that delta xk transpose A delta xi is 0 for I less than k. Now, if that A were not there, we'd say that delta xk, delta xi were orthogonal, but they're not orthogonal. Instead, we call them a-orthogonal. So it's a different notion of orthogonality. We also say they're a-conjugate. So that's another term for it, which is part of how the conjugate gradient method gets its name. Now, these delta x's are very important because they are the steps you take to get from one iterate to the next. They're referred to as search directions. So what this means is the directions that you take to get from one iterate to the next are all independent of each other, literally linearly independent, and they're not orthogonal. You're not always covering entirely new ground, but they're orthogonal in a certain sense. So what that tells you is that each iteration is productive, and that it's covering new ground within the whole space that you're searching for a solution. That's very important. By contrast, steepest descent, you can have search directions being parallel to previous search directions, very unproductive iterations. That's what we like. We like to have independent search directions. The ideal independence is orthogonality. That's really hard to achieve. So we fall short of that, but at least we have this. And if A is preconditioned really well, then it almost is like orthogonality. Yeah.
When we substituted delta RK in the above condition, why didn't we transpose A as well? Because
Asymmetric. So don't need to transpose. So I guess we can say we did. Yeah. Yeah. Well, let's check. It tells me I'm not going to get through this whole thing, but I'm not sure if I need to be concerned about that either. Okay. Now, all right. So what we do is to define our iterates. First, any questions about what we have here? Okay. Okay. So But the key steps of the constant gradient method follows: xk plus 1 is equal to xk plus, now what we had here before was delta xk, but what we're really going to have is some scaling constant alpha k times dk, where dk is referred to as a search direction. Okay. Now, how do we define the search directions? dk is equal to the residual rk plus another scaling constant beta k times the previous search direction. Okay. So those are the main steps that define the constant gradient method. The only thing I've left out is how do we get to scaling constants alpha k and beta k? All right. So I'll write those down. Alpha k is defined to be best possible formula. RK transpose RK over DK transpose ADK. And the reason for this formula, I won't take the time to drive it now, but it is in the notes. It's chosen to enforce the A orthogonality of the search direction, dk. So in other words, really what you could do is you can work with this equation right here, and like you take a inner product of both sides of the right thing, you can require that dk transpose A dk minus 1 must be 0. You can use that to solve for, oh, actually, oh, no, it's this equation. The equation has the alpha k. Well, you also have the other, let me make sure I have this right. Oh, okay. Okay. Really, both equations come from this. The A orthogonality of search directions and the regular orthogonality of residuals. So the formula for beta k is RK transpose RK over RK minus 1 transpose RK minus 1. So it's the norm squared of a current residual divided by the norm squared of a previous residual.
The search direction. What does it represent?
Sorry, what?
The search direction.
Oh, so the idea is to get from xk to xk plus 1, you're going to you're going to start, starting from xk, you're going to go in this direction of dk to find xk plus 1. So it's kind of like you're doing a line search in a way. And the question is, how far do you go into that direction? That's where alpha k comes in. But the way you choose alpha k is to make sure that these vectors maintain their orthogonality relations. Okay. Um, yeah, I better not go into the steps or I'll mess it up. All right, but a key aspect of property of conjugate gradient as a whole is conjugate gradient is designed to minimize this function e of x equals 1/2 x transpose ax minus x transpose b. So this function is minimized when a times x is equal to b. So in fact, if you were to take a gradient, so a gradient of b is ax minus b, which is negative residual. Now you may remember from multivariable calculus that the negative gradient is the direction of steepest descent. So if a method of steepest descent simply uses this, uses r as the search direction. So if I just let this term out, I would have steepest descent. But steepest descent doesn't work well when a is ill conditioned. And that's why conjugate gradient you can think of as a fix to steepest descent by adding on this term. That's where the name conjugate gradient comes from. So each search direction is basically a gradient with a term corrected to make it a conjugate, thus a conjugate gradient. Just clever naming these people have for their algorithms. Okay. Now, the other property we can state about the conjugate gradient is it is guaranteed to converge in n iterations. It's because of the orthogonality of residuals that at some point you've used up the whole space, residuals are orthogonal to everything. The only way that can be is if it's 0. So, thing is, when conjugate gradient was first invented, which was in 1952, we didn't think of it as an iterative method. We actually thought of it as a direct method on the lines of Gaussian elimination, because if you ran it from a whole n iterations, you would have the exact solution. Now, in practice, unless A was really well conditioned, it wouldn't work so well to run a full n iterations because of accumulation of round-off error and things like that. So really conjugate gradient wasn't really thought of as a big deal back then. But later, when people were interested in solving large sparse systems, they saw that, okay, you have guaranteed convergence in n iterations, but you could converge to a bit of decent tolerance in a lot fewer than n iterations. And if an iteration can be fairly fast, if A is sparse, then it attracted a lot more interest. So this is what happens sometimes, is that sometimes the methods are developed in the current computing environment. They may not really get much attention, but computing environments change. And methods that were once thought of as impractical now become practical. Same is true of like methods that are parallelizable. Before we had a lot of parallel computing going on, or any parallel computing going on, certain methods might have been ignored. But if they could perform several operations simultaneously, like the Jacobi method, for instance, now that there's a whole lot of parallelism going on, they get renewed attention. So something to keep in mind is that sometimes maybe a bad method is really a good method whose time has not yet come. And that's what gives me hope about my own research program. So, okay, so, alrighty. I think pretty much, I am out of time. So, definitely the right decision to not go for all the manipulations of how these were derived. But if you really want to, you can check the notes. Or if you take my Math 610 next semester, numerical linear algebra, I will certainly cover it then. Okay, so undefined problems next time, and you go ahead and go homework.